Just picture this for a second.
Okay.
You're outside, you're looking up at the night sky, and you're staring at this tiny, twinkling dot of light that is just millions and millions of miles away.
Right. There's a speck.
Exactly. Just a speck against the absolute blackness. But imagine looking at that speck and knowing, like, for absolute certain that something out there is breathing.
Oh, wow.
Not just existing as some cold, dead rock hurtling through the void, but actively, dynamically changing its world.
That is quite the image.
It really is. And welcome back to Stellar Lab, by the way. Today, you and I are going on a deep dive to decode the cosmic blueprints from our latest source materials. We're looking for those chemical fingerprints, the atmospheric anomalies, and, the structural echoes that actually prove a distant world is alive.
Yeah. And this is, it's such an exciting topic because it's the ultimate pivot from science fiction to rigid empirical science.
Right. No more Hollywood stuff.
Exactly. I mean, for decades, the public consciousness has just been totally hijacked by this search for extraterrestrial intelligence. We have this hope of intercepting a stray radio broadcast or maybe a rover digging up a literal fossilized bone on Mars.
Like a silicon-based femur or something.
Right, exactly. But astrobiology, which is the study of the origin and distribution of life in the universe, it operates on a completely different paradigm.
Okay, so what is the paradigm then?
Well, we're looking for how biological systems fundamentally hijack and really permanently alter the thermodynamics of the environment they live in.
Okay, let's unpack this.
Yeah.
Because I think the best way to understand what we're looking for out there is to basically hold a mirror up to our own planet.
That's the perfect starting point, yeah.
So if some alien astronomer sitting in their civilization, dozens of light years away from us, and they point their telescopes at our solar system, I mean, they are way, way beyond the resolution limit to see our cities or, like, our satellites, right?
Oh, absolutely. They just see a single pixel of light.
Right. That pixel, according to the sources we're looking at today, that pixel is screaming that it's inhabited.
It is screaming, and it's screaming because Earth is chemically anomalous.
Anomalous how? Like, what makes it so weird?
Well, going back to the 1960s, James Lovelock was actually working with NASA on how to detect life on Mars. And he realized something brilliant. He realized you didn't even need to land a probe to know Mars was dead.
Wait, really? Just from looking at it?
Yeah, you just look at the atmosphere. If you view Earth through the strict lens of inanimate chemistry, just normal thermodynamics, our atmosphere is an impossible mixture.
An impossible mixture, because rocks and sunlight don't maintain a chaotic brew of highly reactive gases, right?
Exactly. They burn out. Left alone, non-living chemistry settles into a low-energy state.
So a dead planet is a stable planet.
Yes.
Yeah.
Look at Mars or Venus. Their atmospheres are totally dominated by carbon dioxide. They are in chemical equilibrium. Earth, on the other hand, is completely unstable.
Right, because of the oxygen.
Oxygen and methane, specifically. In our air, they should react and scrub each other out within, well, a few million years.
Which brings us to the formal definition of a biosignature, right? Which is really the cornerstone of this whole deep dive.
It is. A biosignature is defined as any substance, element, or pattern that provides robust scientific evidence of past or present life.
And it does that primarily because it defies that abiotic geological equilibrium we just talked about.
Exactly. The source text actually describes this beautifully. It says, biology enacts a hostile takeover of a planet's natural chemistry.
A hostile takeover. I love that phrasing. It doesn't just adapt to the environment, it engineers it.
Right. It hijacks the carbon, the nitrogen, the oxygen, and cycles them through these massive biological engines.
Because when we normally talk about life, we usually think locally. A forest over here, a coral reef over there. But what astrobiologists are hunting for is biology as a planetary scale geological force.
Which, of course, introduces our primary engineering challenge.
The distance.
Exactly. We've established that a biosignature is a planetary scale disruption. But how do we actually detect that disruption across interstellar distances?
Because we can't just zoom in on the surface of these exoplanets. The contrast ratio is, devastating?
It's completely devastating. The host star completely washes out any optical light reflecting off the planet.
It's like we're dealing with a firefly fluttering next to a military searchlight.
Yes.
But viewed from a whole continent away, the optical noise is just overwhelming. So how are we extracting atmospheric data without being totally blinded by the star?
We rely on a technique called transit spectroscopy.
Okay, walk me through that.
Basically, we wait for a specific geometric alignment. We wait for the exoplanet to pass directly in front of its host star from our line of sight.
So it blocks the light.
Exactly. The
Yeah.
bulk mass of the rocky planet blocks the starlight, creating this tiny, tiny dip in luminosity. But the real magic happens in the planet's atmosphere.
In that thin little halo of gas around the edge.
Right, the atmospheric annulus. The starlight actually filters through that thin fringe of atmosphere before it continues its journey all the way to our telescope mirrors.
Oh, wow. So the star is basically backlighting the planet's air.
That is exactly what it's doing. And as those photons of starlight pass through, they interact with the molecules in that atmosphere at a quantum level.
Okay, so different molecules do different things to the light.
Yes, because different molecules have different vibrational and rotational energy states. So when the broadband, continuous rainbow spectrum of the star passes through the gas, specific molecules absorb very specific wavelengths of light.
Like plucking specific notes out of a musical chord.
I love that analogy, yes. They leave dark absorption lines in the spectrum. We call them Fraunhofer lines.
So when we gather those photons here on Earth and we disperse them through a spectrograph, we can actually see those missing wavelengths.
We do. So if we see missing lines at, say, 1.4 or 1.9 microns, that tells us water vapor is there, actively swallowing up that specific light.
And if we see missing lines at 3.3 microns?
Then we know we're looking at methane. We are quite literally reading the chemical barcode of an atmosphere trillions of miles away just based on the shadows cast by its molecules.
That is just mind-blowing. But let me push back on this a little bit, though, to test the theory.
Sure, go for it.
Let's say we read the barcode, right? And we see really strong absorption lines for carbon dioxide and maybe liquid water vapor.
Okay.
If we announce we found an ocean world with a thick CO2 atmosphere, the media is going to lose their minds. The headlines are going to say, we found a habitable Earth twin, aliens confirmed. But based on our definition of a biosignature, that's not actually evidence of life at all, is it?
No, it really isn't, and that's a crucial distinction. Finding a habitable environment is entirely different from finding an inhabited one.
Right, because water vapor and carbon dioxide are completely abiotic. They don't need life to exist.
Exactly. Think about geothermal heat. It drives volcanism, and volcanoes outgas massive amounts of CO2 and water.
Or comets crashing into the planet.
Right. Cometary bombardment delivers tons of volatiles. Or you can have photochemistry in the upper atmosphere altering cloud compositions. You can easily have a perfectly dead, totally sterile rock covered in vast oceans and thick clouds.
Which means we need a much more sophisticated filter than just looking for water. And that brings us right back to that concept of chemical disequilibrium as the ultimate cosmic red flag.
Yes, let's use the closed room analogy from the source material because I think it paints the picture perfectly.
Okay, set the scene for us.
Imagine you walk into a sealed room and your sensors tell you there are high concentrations of a really flammable gas, like methane or hydrogen.
Okay, so far, so good.
But then you notice it's coexisting in that same room with a dense concentration of molecular oxygen.
Oh. Well, the thermodynamics of that room are basically a ticking time bomb.
Exactly. The moment there is an activation energy, like a spark, or honestly, just given us time, they're going to violently react.
They'll just combust and reach equilibrium as water and carbon dioxide.
Right. So the fact that you are measuring them simultaneously, in high amounts, means something is fundamentally broken with the physics of that room.
Or someone is actively pumping them into the room.
Yes. The only logical deduction is an active, continuous source pumping both of those gases into the environment orders of magnitude faster than they can destroy each other.
So when we scale that room up to the size of an entire planetary atmosphere, the gold standard for that continuous pump is biology.
It is. Oxygen and methane shouldn't be caught dead together.
Because oxygen is just so aggressively corrosive, right? It binds with almost everything it touches.
It does. Think about this. If the biosphere on Earth were to just suddenly undergo a mass extinction tomorrow, and all biological activity cease completely.
Like plants, algae, everything just stops.
Everything. Our 21% oxygen atmosphere would just vanish. In a geological blink of an eye, it would be gone.
Really? Where would it go?
It would react with the iron in the crust, essentially rusting the surface of a planet, and it would bind with volcanic gases. The only reason it persists at 21% is because photosynthetic organisms are constantly churning it out.
They're treating it as a biological exhaust gas, constantly replenishing it.
Exactly. And then on the other side of the ledger, you have methane.
Right. Methane is unstable too. It gets destroyed by photolysis,
Yeah.
right? Like ultraviolet radiation from the sun literally tears it apart.
It tears it apart, and it also reacts rapidly with the free oxygen we were just talking about.
Yet Earth maintains a steady trace concentration of methane in the air.
Yes, and that is primarily due to methanogenic archaea and bacteria, organisms operating in anaerobic environments.
Like deep ocean vents and wetlands.
Deep ocean vents, wetlands, and even the digestive tracts of ruminants like cows.
Cows. Right. So what's fascinating here is that the search for life is actually the search for a planetary conflict.
That's a great way to put it.
You are looking for an atmosphere that is locked in this eternal chemical standoff. The gases are constantly trying to burn each other out, but the biological engines on the surface refuse to let the planet rest in peace.
It's an ongoing dynamic process. But, and this is a big but, as compelling as the coexistence of O2 and methane is, we have to be incredibly careful about false positives.
Because geology can be tricky.
Very tricky. The universe has a wicked sense of humor, and it is highly adept at mimicking biological signals through really complex abiotic pathways.
Right, because if we're going to stake the greatest discovery in human history on a few missing pixels of light, we have to rule out geology completely.
100%.
So, play devil's advocate for me. How could a dead world generate an oxygen-methane standoff without any life?
Okay, let's start with the methane. Methane can be produced abiotically through a geological process called serpentinization.
Serpentinization. Sounds ominous.
It basically happens when water interacts with ultramafic rocks like olivine deep down in a planet's crust.
Okay, so just water and rock.
Right. The oxidation of the iron in those rocks generates hydrogen gas. And then that hydrogen can react with crustal carbon dioxide to form methane.
Ah, I see. So if a planet is highly geologically active, it could constantly be venting this abiotic methane into the sky.
Exactly. No cows or bacteria required.
But what about the oxygen? Because to get that disequilibrium red flag, you'd still need the oxygen to be there too.
Right, and that's where photochemical reactions can completely deceive us.
Why so?
Imagine a planet orbiting very close to a highly active star. The planet is getting hit with massive doses of ultraviolet radiation.
Okay.
That UV energy hits the water vapor in the upper atmosphere, and it actually splits the H2O molecules apart.
So it separates the hydrogen and the oxygen?
Yes. And hydrogen is very light, so it reaches escape velocity and bleeds off into space. But the heavier oxygen gets left behind.
Wow. And it just builds up over time.
Exactly. So suddenly you're looking through your telescope and you see a completely dead planet with a high oxygen atmosphere and geothermally vented methane.
That is a terrifying false positive. I mean, it implies that just finding the gases isn't nearly enough. We really have to contextualize the entire planetary system.
We do. We need to know the stellar radiation output, the mass of the planet, the escape velocity of its atmosphere. Context is literally everything in astrobiology.
So a biosignature is never just a single data point. It sounds like it's a holistic argument.
Exactly. Biological activity is only the surviving hypothesis after you have rigorously, meticulously murdered every abiotic alternative.
Wow. Okay, so we've spent all this time talking about distant atmospheres, the extreme difficulty of interpreting photons across light years.
Right.
But what happens when we drastically shrink the distance?
Yeah.
Like, what happens when we can drop a physical payload directly onto the surface of a target?
You mean like the Martian regolith or the icy crust of Saturn's moon? Enceladus?
Exactly. We have rovers on Mars right now. The methodology completely inverts, doesn't it?
It does. We transition from atmospheric transmission spectroscopy to in situ chemical and physical analysis. We are no longer hunting for transient gases. We are hunting for durable, complex molecular architectures that are locked in the ice and rock.
And here's where it gets really interesting based on our source text. When we talk about organic molecules on these worlds, we have to aggressively clarify our terms.
Oh, absolutely. This causes so much confusion.
Right, because in the public lexicon, the word organic implies a biological origin, like organic apples at the grocery store.
Right, but in chemistry, organic merely means the molecule contains carbon.
And the universe is absolutely overflowing with abiotic carbon, isn't it?
It is everywhere. We find complex organic chemistry in the interstellar medium. We find it in the Murchison meteorite.
Wait, a meteorite?
Yeah, the Murchison meteorite is actually packed with amino acids that formed in the deep freeze of space billions of years ago. Non-biological processes synthesize these